Hello, the genius. All right, welcome back to day three. So we are studying the story of understanding the history of computers, how computers were bettered. So we are getting closer to electronic computers. Okay. So today we'll talk about the birth of electronic computers. Remember, the computers that we are using today are electronic. The first computers that came on board were human beings. After human beings, there were manual computers. After manual computers, there were mechanical. Then we got to electromechanical, and we got to electronic computers. So let's take a look at how these things grew. So we'll talk about the electromechanical computers, the ZOS Z3 and Harvard Mark One. We'll talk about the electronic computers, the ENIAC, EDVAC, and UNIVAC. We also talk about the role of World War II. All right, because the World War II really helped in making computer evolution faster because then the government invested money to actually fund the research. So World War II really helped in the growth of computers. Okay, so we'll talk about the transition from vacuum tubes to transistors. I still want you to understand something. You don't need to cram any of these things. These are not the things we discuss these days, but we just want you to understand. You don't need to cram that ENIAC, Colossus. We don't need to vacuum tubes. You don't even need to know what they are, but you just need to understand. We are telling this story because we want you to understand how computer has grown over the years. Okay, so before the 1940s. Most computers were either mechanical, using gears, levers, or cranks, all right, or electromechanical, all right. So some mechanical components combined with electrical relays. So the ones that are electromechanical, they have some mechanical components that were combined with electrical relays. So like I said, you don't need to know what an electrical relays is. Okay, just understand the growth of computer here. So why they could perform calculations. So now this is what you should understand. The reason why they were created, the reason what they do and stuff like that, and why they have some limitations, okay, and why there were better computers created after them. So the electromechanical computers, all right, they could perform calculations, but they were slow, bulky, and limited. So of course, they could perform calculations better than the abacus. All right, they could perform calculations better than the Pascaline, the Napier's bones, and stuff like that. But they were still limited. The thing is that human beings crave for more. When we do something that is even better than the one that we did yesterday, we would want to crave for more and do better than that one. Okay. So the birth of electronic computers marked a monumental leap. All right. So the birth of electronic computers, when we started using electronic circuits powered by vacuum tubes instead of mechanical moving parts, they allowed these machines to perform calculations thousands of times faster. So basically, what this phrase is saying is this. Electronic computers were faster than mechanical computers. That's just the basic here. All right. Electronic computers, which is the one we are using today, they are faster than mechanical computers. All right. So the first electronic computers, they started using something we call electric circuits. All right. So we are going, as you grow, you get to understand all these things. All right. So they use something we call electronic circuits. And these electronic circuits were powered by vacuum tubes. Vacuum tubes are like switches. Like the switch, you have switches on. Look around the room that you are in right now. You must see a switch. You must see a switch. If you put the switch on, there will be light. If you put it off, there will be no light. So that is how these vacuum tubes were working. They were working as switches. All right. So the first electronic computers were using vacuum tubes. All right. So now let's take a look at the technological leap from relays to vacuum tubes. Remember, from mechanical computers, we got to electromechanical computers. So electromechanical computers were using both mechanical components and electrical relays. So that made them electromechanical. So electronics plus mechanical materials, components. But now we are looking at from the electric relays to vacuum tubes. Vacuum tubes are switches, so they were used to build purely electronic devices. But the relays were used to build electromechanical devices. All right. So, like I said, if you do not understand anything, no problem. You don't need to cram anything here. Okay. So, mechanical switches found in early machines. They were found in early machines like analytical engine or punch cast systems. So there were mechanical switches, all right? They were found in analytical engine. Remember, it was Babbage that designed this analytical engine. They work by physically moving parts to open or close a circuit. So these mechanical switches, they worked by somebody has to move the parts to open it or close it. Just like now, the way your socket, your switch is on the walls. If you open it, uh, if you open it, there will be no current flowing. If you close it, there will be current. Just try your switch. All right. When you close it, there will be current. When you open it, there will be no current. So that is how the mechanical switches were working. So electromechanical relays, they were used in machines like the Conrad Zeus Z3. We will still talk a bit about it. Okay, so these were electromechanical computers. The Z3, the Conrad Zeus is the creator of Z3. So Z3 is an electromechanical machine. All right, it's an electromechanical machine. So these were electrically controlled switches. So these electromechanical relays, they were controlled switches by they use electricity to control the switches. All right, but the mechanical switches do not use electricity to control the switches. It is physically moved, all right, to do open and close. But the electromechanical relays were using electricity to control the switches, and they were faster than purely mechanical parts. So these electromechanical relays that are switches, they are faster than mechanical switches, but they still have some limitation by the time it took to physically move contacts. Of course, there will still be limitations. So from there, because of they wanted to build something better, vacuum tubes were created. So these vacuum tubes, they are glass tubes that could control electron flow with no moving parts. Do you understand? With the vacuum tubes now, there was no need for any physical uh, moving parts. They act as switches and amplifiers, enabling much higher speeds. Don't bother about yourself. Don't bother yourself about all these things, all these terminologies we are using now. All right. I believe you do not, you might not even know what switches are. Some of these things are taught in physics and maybe in the university. So don't bother yourself too much if you do not understand some of these things I'm saying here. Okay, but just grab as much as you can grab. All right. So this shift meant calculations could be done in milliseconds instead of seconds. So you can see with the use of vacuum tubes, calculations were faster. So calculations could be done in milliseconds instead of seconds. Okay, so it was really a big growth. So let's talk about the pioneers and their machines. So who are the people who paved way for electronic devices? Okay, let's talk about them and the machines that they created. Conrad Zuse and the Z3. So Conrad Zuse is the pioneer or the developer or the creator or the inventor of Z3. Z3 was created in 1941, and this Konrad Zuse is a German. So this machine was created in Germany. The Z3 was the world's first programmable digital computer. Now, let me explain to you what we mean by being programmable. If you can remember, the first computers that came they were only used to do addition and subtraction. All right? So they were only used to do one particular thing. But as analytical engine came, Ada Lovelace found out a way to make it programmable in the sense that you can program it to do different things for you. You can say, okay, do addition for me or do multiplication for me. The same machine. So one machine can do addition, subtraction, division, logarithm calculations, and anything like that. So, but you have to now program it. That is why Ada Lovelace was seen as the first computer programmer. So, as a computer programmer, you can tell the computer exactly what you want it to do for you. And these days now, the computers that we use are very, very sophisticated that they can do so much. So many things, okay? So you can program it to do so many things. All you have to do is to write the program. So, like I said, if you do not understand this and I just said, as we go on, you'll get to understand these things better, okay? So, technology that was used to create this Z3, this Conrad Zuse used electromechanical relays, not vacuum tubes. But this laid the foundation for electronic designs. So electromechanical relays laid foundation for electronic designs. All right. So you can say that electromechanical relays are the father of electronic designs. Okay, because it was through the work of electronic relays that electronic designs were made. So what is the significance? It introduced binary arithmetic and stored programs in punched film. So basically, this Z3 introduced binary arithmetic. Binary arithmetic is the zeros and ones. Don't worry, we'll teach you binary arithmetic in a later class. You're going to understand binary arithmetic. And binary arithmetic is what the computer uses. The computer does not use decimal arithmetic. Okay? Just grab as much as you can grab from this class. All right. Most of these things I'm saying, you might not even need it. All right. I don't even remember all these things. All right. So, but when we get to the place you will need to really remember, we'll let you know. But for now, just enjoy the story that we are telling. Okay. So, what was the impact of the Z3 machine? Although it was destroyed during the World War II bombing, all right, it was destroyed. So even though it was destroyed, it proved that general purpose programmable computers were possible. So when we say general purpose programmable computers, we mean that one computer can be programmed to do many things, not just only addition or subtraction. A computer can be programmed to do video editing. A computer can be programmed to do image processing. A computer can be programmed to store data. So this Z3 gave some people inspiration, proving that general purpose programmable computers were possible. So let's take a look at the second one, the Colossus. Colossus was designed in Britain in 1943 to 1944, right? But the purpose it was to help Britain in the World War II. All right. So it was designed by engineer Tommy Flowers to break Lorentz encrypted German messages during the World War II. So the thing is that from Germany, somebody, Lorentz, was sending messages that were encrypted. When we say a message is encrypted, we mean that when you encrypt a message, somebody else reading it will not understand it. So Lorentz would send a message in an encrypted format. Then Tommy Flowers created the Colossus so that he can use it to decrypt it. It's okay if you don't understand these terminologies. All right. As you continue this your journey, you get to understand what we mean. Okay. So when you encrypt a message, somebody else will not understand that message. But another person that has the key to decrypt it will use the key and decrypt it and understand what you sent. So that is how it works. So this is used in cryptography. This is used especially in cybersecurity. All right. So technology that was used in this Colossus, they use vacuum tubes to process data at unprecedented speed. So the data processing was very, very fast. So instead of using electromechanical relays, this guy, Tommy Flowers, used vacuum tubes, and there were 1,500 of them. All right. So in this case now, computers were becoming electronic, purely electronic. So what were the capabilities? It could encrypt messages from punched tape at high speed and help decrypt them using pattern analysis. So from what we are saying right now, you can see that this Colossus was not a general purpose computer. It was designed for one particular purpose. It was to help the government of Britain to decrypt and encrypt messages. So it wasn't a general purpose computer. Okay. So it was classified using until 1970s. All right. So the British government did not release it. It was a secret. Okay. So it was not in the public. So it was a secret till 1970. So its role in computing history was hidden for decades. So this computer was sponsored by the British government. So they did not make it public so that people would know about it. So they were using it during the World War II to fight. All right, so let's take a look at the third one, the ENIAC, Electronic Numerical Integrator and Computer. So this one they started building it in 1945 and they finished it in 1946. So this one was in the USA. Okay, so who are the developers of this computer, the ENIAC? John Presper, Eckert, and John Mauchly at the University of Pennsylvania. Okay, so these are the developers of this electronic machine. So this machine contained 18,000 vacuum tubes. Remember, the Colossus contained 1,500 vacuum tubes, but this one contained 18,000 vacuum tubes, and the weight was 30 tons, and it consumed 150 kilowatts of power. It was very big. It was as big as a room. It was very, very, very big, and it could consume a lot of electricity, a lot of power. Okay, it could perform 5,000 additions at the same time per second. It can perform 5,000 additions, something like arithmetic operation. It can do 5,000 additions in a second, or it can also do 357 multiplications per second. So it was a massive leap over previous machines. So this was a massive growth. Computers started growing from here. So now it was also programmable. All right. So initially, it required manual rewiring and switch setting to change the task. I wouldn't want to bore you with this thing. You don't even need to understand what it is. But don't worry, as you grow, you get to understand this. Okay. So it required manual rewiring. Okay. So you have to manually change the wires of the switches. So you take wire from this switch and put it in another. So let's say now if you want to do addition, all right, there's a way the wire for there's a way they wire it for you to do addition. So if you want to do multiplication, you have to change the wiring and the switches and plug it again for the multiplication. So that's how the programming was also done. So, but what was the impact? It was the first general purpose. Remember, the Colossus was specific. It was not a general purpose. It was a specific purpose computer. But this ENIAC was the first general purpose, fully electronic computer capable of solving a variety of problems. So this was a very big one, a very big growth. So what are the key features of electronic computers? Binary and decimal arithmetic. So they were able to do binary and decimal arithmetic. Early designs varied. Z3 used binary, while ENIAC used decimal representation internally. But the thing is this, generally, computers these days, they use binary arithmetic. All right? So the programmability, some were hardwired for specific tasks, just like the Colossus, while others allowed reprogramming for different calculations, the ENIAC, okay? So the speed, moving from mechanical switches to electronic circuits, reduced the computation time drastically. That means they were faster in solving problems. the size and the heat. Large and hot vacuum tubes generated enormous heat and often failed, requiring constant maintenance. Now, if you touch the back of your computer now, you will notice that it is hot. All right, that part of your computer that is sitting on your table now, just raise it up a bit and put your hand on that. You'll see that it is hot. The thing is that even though that modern computers don't use vacuum tubes, they use integrated circuits, transistors. Computers still produce heat, but the heat they produce now is smaller than the heat it was producing those days. So those days, the heat was very large and hot. Okay, so what is the historical context? The World War II was a very big catalyst. The World War II, the urgent need for faster calculations in ballistic, cryptography, and logistics pushed government to fund computer research. So because of the World War II, government were investing and funding computer research. And because of the computer research, computers were made faster. So collaboration between military, the engineers, and mathematicians, all right, helped influence the design approaches. So post-war, after the war, now these technologies rapidly moved into scientific research and business application. So the ENIAC, the Colossus, after the war, all right, since the government was funding the Colossus so that they can actually use it during the war, when the war ended, technologies rapidly moved into scientific research. So people started researching on those technologies that were used during the war to build computers. And that is why we have a very good, we have computers amazing today. So the birth of electronic computers directly led to stored program architecture. There's something we call stored program architecture. Now, I will just throw a little light. Okay, if you don't understand it, no problem. You will get to understand later on. I told you about the ENIAC. If you want to do addition, you have to change the wire and the switches. If you want to do subtraction, you change the wire and the switches. If you want to do multiplication, you do something like that. But when we talk about the stored program architecture, it means that the program for doing addition will be stored in the computer. That's the computer you're using today. After writing a program, you store the program inside the computer, and you can tell the computer when you want the computer to run that program. So that's what we mean by stored program. So computer programmers will now write the program and then store it inside the computer. And the computer, and when a user clicks the mouse, like now your mobile phone, when you tap on any of the programs, like maybe your WhatsApp or your game, all right, those are stored program in your phone. So when you tap it, the program will run. So that's what we mean by stored programs. All right. So these programs now can now be stored inside a computer. So it was created, the concept was created by John von Neumann. Okay, he is the first person that created the stored program architecture, proposed it, and it was later implemented in the EDVAC computer. There is also something we call miniaturization. Miniaturization simply means as the computer was big, the ENIAC was a very big computer. Scientists started working on making this to reduce the size. So imagine a computer that was as big as the whole room that we have here. Imagine a computer that was as big as a full room. Now you can have those computers on your palm, on your mobile phone. Just imagine. So this is what we call miniaturization, and they eventually replace vacuum tubes with transistors. Okay, so don't worry, we'll talk about these things as we go. All right. So modern science, computer as a distinct academic field. So these are the things that the birth of electronic computers influenced. Okay. So many principles like the binary logic, programmability, automation, they remain at the core of all computing today. So all these things were as a result of the birth of electronic computers. Okay. So when you take a look at what we have here, in the year 1941, Z3 was created in Germany. It used electronic relays. So electronic relays, the Z3 is considered to be the first programmable digital computer. In 1943, Colossus, all right, was created in Britain, all right, and it used vacuum tubes. It is it is recognized as the first programmable electronic computer, but it was special purpose. It was only used for the government for encryption and decryption. Then in 1945, we now had the ENIAC that was developed in USA. So it also used the vacuum tubes, and then it was the first general purpose fully electronic computer. So this is the story so far. All right. So what's the key takeaways? The move to fully electronic design was the turning point in computing history. All right. It changed everything, moving from electromechanical to electromechanical, from electromechanical to electronic design. It changed a lot of things. Then the wartime pressure accelerated innovation. So during the war, innovation was accelerated because government needed to fight war using computers. So they invested in a lot. They invested a lot in computers. So, though massive and inefficient by today's standard, these machines, although they are no longer used or they are inefficient right now, they proved that high-speed automated computation was possible. So, setting the stage for modern computers. So, you can see this is the contribution or the significance of electronic, the olden days electronic design of computers. So, thank you very much. If you have any question, please reach out to us. Just do your test, do your test, okay? I will see you in the next class. Thank you very much.